So if there is some way to calculate delta G, then there's probably going to be some way to relate this to eventually an equilibrium constant, equilibrium expressions as well. Now these equations that I have posted here, I just want to talk briefly about. The good news is this second one, we're going to do more from a standpoint of Le Chatelier's principle. We're not going to use that equation. It's known as the Nernst equation. It's definitely used in some chemistry courses. AP Chemistry a few years ago decided to do more of a qualitative approach to it. So I'll mention, what kind of happens with regard to this, and I'll show you the qualitative way to go about this. So here is our non-standard Gibbs free energy, is standard Gibbs free energy plus R, 8.314, times the temperature in Kelvin, times the natural log of Q, the reaction quotient. Remember, Q is like K, we just don't know if we're at equilibrium. So we set it up the same, plug in those concentrations. Of course, the good news is, for our equation here, if everything is 1 molar, then this is going to be 1 and E is E standard. So in this Nernst equation, if this value is 1, the natural log of 1 is 0, so all of this is a non-factor, meaning that's the standard value for the EMF, the standard voltage. But what if we want a non-standard voltage? What if we change those concentrations? Well, if we change those concentrations, we can plug them into this equation and we can get the new value. And it could take that let's say 1.10 volts, and it could decrease it. If this whole factor here is positive, we subtract it, it's going to go down, or it could increase it. And it all has to do with this value here. Now again, the good news is, from a standpoint of Le Chatelier's principle, I'll explain how to do that. R, 8.314, T, our temperature value there in Kelvin, N, the number of moles of electrons, F, Faraday's constant, 98,485, natural log of Q. So we could plug in those equilibrium values and we could solve for that as well. We could find an actual number for that. The second one, if it's at 25 Celsius, they've cleaned up the numbers a little bit, since this is a constant and this is 298 and this is a constant. They've simplified R, T, and F into 0.0591 over N, and this is probably the more common form of the Nernst equation. Most of what we do is at 25 Celsius with that. So now we've kind of crashed our Gibbs free energy and equilibrium and all of this in together, and ultimately, when Q and K are equal, then we're at a point of equilibrium. And at equilibrium, the cell EMF is 0. So we say that the battery has died, but there's just not enough force to push the electrons anymore. Actually, the battery doesn't die. The battery reaches a point of equilibrium. At that point, there's 0 voltage. So, and also at that point, delta G is 0 because we're at that part we call equilibrium. So again, here's how all of this kind of comes in together as one. Now let's look at some questions here real quick. And the first one I want to do more from a standpoint of qualitative. If I have 2 Al solid plus 3 manganese 2 ions aqueous, forming 2 aluminum 3 aqueous ions and 3 Mn solids, and it gives me the values 0.48 volts. Again, we could look those values up and we could find them, and the coefficients we don't have to worry about. The 3 and the 3, we just look up the value for Mn++ plus 2 electrons to Mn. Again, we get that reduction value. Don't triple it because it's a joule to coulomb ratio, so both triple, so the value stays the same when we look it up. And the aluminum here is being oxidized, so we would have to change the sign because we're going to find a reduction value. But again, someone's already done that for us, and they've given us this value of 0.48 volts. And then we encounter a question that says, okay, what if we change the aluminum ion concentration from 1 molar to 2 molar? We're going to leave the manganese ion at 1 molar, but we change that aluminum to 2 molar. We've increased the amount here. Well, here's the good news. We can do this in terms of Le Chatelier's principle. If we increase this concentration, it's going to counter that disturbance. It's going to move back. That voltage is going to be lower. It's going to be less than 0.48 volts. And I'll do that math-wise here in just a moment. I'll show you that calculation. On the other hand, if we leave the aluminum at 1 molar and we change the manganese to, for instance, 2 molar, then that's going to drive to the right. So that's going to increase that voltage. So if I wanted to design this battery and I wanted more than 0.48 volts, I've got some options. One is maybe I go with manganese ion equal to 2.0 molar. Or, on the other hand, we've talked about just comparing these to 1. It would have the same effect if I change the aluminum ion from 1 molar to 0.50 molar. Or what if I do both? So again, if I do both of those by increasing this and decreasing that, it's going to shift this to the right, and that's going to increase the voltage. Now, if I do that at 25 Celsius, that's where that second equation that we worked with a moment ago comes in. What is the voltage? What is the EMF? Well, it's equal to the standard EMF, 0.48, minus, I picked at 25 Celsius to make life easy here, 0.591 over N. I need to get the number of electrons. So I need to find how many electrons we have involved in this balanced equation. 2 aluminum ion. That's going to be 6 electrons. 3 times 2 here, we're going to have 6 electrons. So my value for N is 6 log of Q. Remember, Q is like K, and the good news is this is a solid and this is a solid, so they're not part of the equilibrium expression. On the other hand, I've got the aluminum 3 ion, so that's going to be 0.5 squared over 2 to the third. And now I'm ready to go ahead and plug those in and solve. So I'm going to work kind of backward through the math on this. 0.5 squared, got my value, 0.25, divide by the quantity of 2 times 2 times 2, which is 2 cubed, which is 8. And now I'm going to take the log of that value. Once I've divided 0.25 by 8, I got 0.03125. And then the log of 0.03125 is, and notice this is a negative value. So by that being negative, when we subtract off that negative, we've already predicted, Le Chatelier says this is going to go up, and it's going to, because when we do this and we have less products and or more reactants, we're going to get a decimal. When we take a log, we're going to get a negative value, and thereby subtracting a negative is going to cause that to increase. So we did it by Le Chatelier's, now we're doing it by the Nernst equation mathematically. The log of that was negative 1.5 times 0.0591, divide by 6 electrons, and subtract that from 0.48. And 0.48 minus that value, I end up with, doesn't change it a whole lot, but 0.49 volts, just with those few changes that we made. Again, by way of AP chemistry, this is a calculation that you won't be asked to do, but you'll definitely have to make predictions as to what's going to happen in terms of the voltage by changing those concentrations. Again, our standard voltage when we do standard reduction potentials, and we look those up, is based on this being 1 molar, this being 1 molar, where we would have the log of 1, which is 0, meaning that's why we call it standard voltage. But non-standard voltage, you got to be able to predict what happens when we change those. And Le Chatelier's principle will allow you to do that.